So we are gonna be doing the finite element formulation of bar element equation, still one-dimensional. Equations. Zoom. Better. Using the principle of minimum potential energy. So first, I would like to write the steps that we're going to take in order to do that. We are going to formulate an expression for the potential energy, pi p. Step number 2, we are going to use shape functions or assume displacement pattern within the finite set of undetermined nodal displacements. And then we are going to obtain a set of simultaneous equations by minimizing this pi p with respect to nodal displacements. So I'm going to start with number 1. Pi p is equal to u plus omega. Pi p is the total potential energy. U is the internal strain energy. And omega is the potential energy of external forces. We're going to be looking at a one-dimensional bar element. So if I'm looking at a bar element like this along the x-axis, so this is x, this is y, and this is z. But we are working, and of course everything is 3D, but if you imagine we are working here in this 3D, and my bar that has a length L extends along the x-axis. It has an area A and is subject to a force F. If I pick a differential element, that has size delta x, delta y, and delta z. This infinitesimal element is going to go through an elongation because it is subject to a sigma x on face x. So if I want to find the force, I multiply the sigma x by the area, which is going to be delta y times delta z. And this face is going to be stretched. Or if I want to look at this change in displacement, I will be looking at delta d epsilon x. Delta x d epsilon x, right? So what I'm looking here, delta x d epsilon x, this is the change in displacement, specifically between the two faces that I'm showing. Change in displacement if I'm looking at face x and x plus delta x. So this is the differential element that we're looking at. Now we start looking at the work done by the internal forces during the formation. And I'm going to refer to this as du. And this du will be equal to the force multiplied by the change in displacement. So the force is sigma x times delta y times delta z. And I'm going to multiply this by delta x d epsilon x. So this portion here multiplied by delta x d epsilon x. Okay. I calculated the force, the internal force on that face, correct? So if the face is subject to stress sigma x, face x in tension, in order to find the force, I multiply it by this differential area, delta y times delta z, okay? Now, in this differential element that has a length delta x and undergoes a strain epsilon x, the change in displacement can be described by the length times the differential strain. So delta x times d epsilon x. So when I'm looking at the work done, I'm multiplying the force times the change in displacement. Okay, so this is du. In order for us to find u, we are going to integrate over the volume. Integrate over the volume. Sigma x d epsilon x dv. As we go, because I have here d epsilon x, so as we go, I'm going to put an integration here sign from 0 to epsilon x. If we are working with a linear elastic material, we can describe the relationship between the stress and the strain using a straight line that has a slope of E over 1. And we can write the relationship sigma x is equal to E times epsilon x. So now if I want to find the integral from 0 to epsilon x of sigma x d epsilon x, you can say that this is equal to the integral from 0 to epsilon x. For sigma x, I'm going to put E epsilon x d epsilon x. This is equal to, E is a constant, and when I integrate epsilon x, I will get epsilon x squared over 2 from 0 to epsilon x. So we get here E epsilon x squared over 2, and epsilon x or E epsilon x is sigma x. So I can also write it as sigma x epsilon x over 2, which, by the way, is the area under the curve, right? So for a specific sigma x and a specific epsilon x, it is the area under the curve, as we've seen before for a string element. Now, U, the integral here that we're trying to evaluate. So U is the triple integral over the volume. Now I can, I have evaluated the integral of sigma x d epsilon x. So I'm going to put sigma x epsilon x divided by 2 dv. Sigma x epsilon x over 2, right? Yeah, because E epsilon x is equal to sigma x. Right. You're welcome. Now, since I have a uniform cross-sectional area A here, so for a uniform cross-section area, when the stress and strain are dependent only on the x-axis, we can go from volume to length by replacing dv by the area times dx. And I'm going to pull the 2 outside, so U would be equal to A over 2. And then I'm going to go from dv to dx, and I'm going to go from 0 to L of sigma x epsilon x. So now we have an expression for U. As far as omega, the potential energy of the external forces. Now, when I look at a bar element, we could have, on a bar element, we could have body forces, traction forces, and nodal forces. So let's say we have a bar element like this. I could have so here is my beginning and my end. I may have a body force or a surface force and nodal forces. So I'm going to express that here. I'm going to call this one acting on the body as XB. This on the surface, I'm going to call it a traction force. So this, I'm going to call it TX along the X-axis. And also, I'm going to have an F1 and an F2 nodal forces. So if I look at these forces, I can find the potential energy of external forces. And these are going to be the body forces, XB, are applied over the volume. So I'm going to get a minus the triple integral of XB multiplied by U dV minus, I have the traction forces applied. So this is integration over the volume. The traction forces are applied over a surface. So I will call it here S1. And I have this TX multiplied by U on the surface, ds, minus the sum of all the nodal forces. So I'm going to call it Fix times their corresponding nodal displacement Ui from I equal 1 to M. Of course, for a bar element like the one I'm depicting here, M is equal to 2, right? For M equal to 2 for a 2-node bar element. Let's define some of these variables. So XB, these are body forces per unit volume. When I say body forces per unit volume here, this is like, for example, gravity, right? Body forces per unit volume. U that comes here is the displacement function over the volume. Tx is the surface loading or traction. Us, this would be the displacement function over the surface. And Fix, these are nodal forces. And Ui will be nodal displacements.
For the body force, isn't it in capital B as well?
I wrote it here. Yeah, I will keep it consistent. Lowercase b.
Make it check.
Sure. Now it's worth noting that XB, TX, and Fix, they all act in the local X direction. So as you can see here, they're all going in the local X direction. So I can label my bar here as node 1 and node 2, and it has a length of L. So what I'm showing here are really general forces. We may or may not have all of these. So now I have an expression for U and an expression for omega. And this was our first step, is to formulate an expression for pi p. Our next step is to assume a displacement pattern within the finite set of undeterminate nodal displacement. So now I'm going to go to step number 2. And when I look at my general 2-node bar element, so we have 2 nodes, node 1 and node 2. At node 1, I have a displacement U1, and at node 2, I have a displacement U2, as we've done before. And we came up with this function, U, that gives us the displacement along the length of the bar as a function of X. So this bar element has a length L and is oriented in the X direction. We were able to express U in terms of the nodal displacements. Now, these nodal displacements, U1 and U2, we call them D, where D is equal to a column matrix of U1 and U2. I was able to express U using shape functions as N multiplied by the nodal displacements D, where this N is equal to, I have 2 nodes and we have 2 shape functions, N1 and N2. We solved for N1 and N2, and we found that N1 was 1 minus X over L, and N2 was simply X over L. If I want to get an expression for US, we are going to evaluate these shape functions for that particular surface, and I'm going to call it NS, multiplied by D. Now, since epsilon x is equal to du by dx, and we have an expression for u, right? So I can say that this epsilon x is equal to d by dx of n d. When I apply the operator here to find the derivative of n, we are going to refer to this as the B matrix. So I can get this general expression that epsilon x is equal to a B matrix multiplied by D, where B is the derivative with respect to x of the matrix of shape functions. In this particular problem, I have n here. So if I take the derivative with respect to x, I will get minus 1 over L and 1 over L. So we have here an expression for epsilon. Now, if I want to write an expression for sigma x as it relates to epsilon x, these are related via the matrix D. For a one-dimensional stress-strain relationship, the matrix D is simply E, the modulus of elasticity, right? E, the modulus of elasticity. Sorry. B is the derivative. Here there is 1 minus x over L. When I took the derivative, I only got minus 1 over L. So this is simply E, the modulus of elasticity. Now, since epsilon x is equal to B times D, we can then say that sigma x, I substitute for epsilon x here, would be equal to D times B times D. So I was able to express sigma as a function of displacement, nodal displacements. And this was step number 2, to assume a displacement pattern within the finite set of the undetermined nodal displacements that we can use to express sigma. Excuse me? Is it what? D is here, is the nodal displacements, U1 and U2. The big D. Here I can use the modulus of elasticity E, which relates the stress and the strain, right? I'm trying to use matrices for a general form so we can use it later on for more or higher order elements. Good. Now, if I go back to my potential energy, total potential energy, okay, we can write the total potential energy pi as equal to A over 2 times the integral from 0 to L of sigma x epsilon dx minus, I'm gonna just rearrange here a bit, the triple, let's copy it first, the triple integral over the volume of x b u dv minus the double integral over the surface S1 Tx us ds plus, I'm sorry, minus the summation from I equal 1 to m of f I x u r. So that's here the expression for the total potential energy. In order to use these, I'm going to write it in matrix form as equal to A over 2 from 0 to L. I want to multiply sigma x by epsilon x, and I'm going to use the matrices. So I'm going to use here, I had a column matrix for sigma x and a column matrix for epsilon x. So in order for me to do this multiplication, we're going to have to transpose one so it stays consistent, dx. Minus, I have the triple integral over the volume. And I have xb times u dv. Now for this sigma x times epsilon x, I'm going to have to transpose sigma x because it's column. So I multiply a row times the column matrix. Here I have xb and u. If I write xb in terms of, or as a column matrix, xb, and u, I'm also going to write it as a matrix here. Again, we're going to take the transpose of u, dv, minus the double integral over a surface S1 times, I'm going to again flip the order. So I'm going to have US times TX ds, and I'm going to put a transpose here for u. And finally, minus I have here Fix times ui. So I'm going to put D, the displacement matrix, transpose nodal displacements, multiply by, and instead of Fi, I'm going to put the force matrix P. So P is the nodal force matrix. Sigma x and epsilon x are column matrices. As a matter of fact, sigma x and epsilon x, as well as, let me write them all here, u tx and xb. These are all column matrices. P. Here, P. Yeah, no, just P is the nodal force matrix. I meant to write these T's in green to let you know that we're taking the transpose for proper matrix multiplication. That's the reason. So the transpose is taken for proper matrix multiplication. Now, what we're going to do next is we're going to substitute for sigma x and epsilon x in terms of B, D, and D, right? So we were able to express them in terms of B, D, and D, we're gonna substitute here in this equation. So we can write pi p as equal to A over 2 multiplied by the integer from 0 to L of sigma x transpose. And for sigma x, we had dB times D. If I take the transpose, I have to reverse the order, right? So I will write it as D transpose times B transpose times uppercase D transpose. And for epsilon, we are going to use B times D. So here this is multiplied by B multiplied by D dx. So this is the first term of my equation.
Not just the last this week, that kind of just be like two-dimensional.
If it is only in one direction, right? And if I'm relating, as you're gonna see here, it's gonna boil down to a 1 by 1. Just bear with me and you're gonna see it, okay? Next, we have here minus the triple integer over the volume. We had the xb, I think I did not put xb multiplied by u. And again, for this one, in order for us to write it, yeah, I wrote it here. Yeah, U transpose times XB. So we're going to start with the U transpose, which is going to be D instead of N times D, we're going to have D times N because we're taking the transpose. So we're going to write this as D transpose times N. And again, N is a row matrix transpose multiplied by the XB dV minus the double integer over the surface of, I have here U transpose. So I'm going to do a D transpose times N evaluated over the surface transpose multiplied by Tx ds minus the last one we have here is D transpose times B. So I'm gonna have D transpose and times P. I hope it's clear here when I put like two column matrices multiplied by each other. We cannot do that. One has to be the transpose. So what I have come up to here is I was able to write pi p as a function of the nodal displacements. And this was the goal, because the next step, we're going to take the partial derivative. So of the nodal displacement or function of U1 and U2. It is worth noting that the function, sorry, the B matrix and the D matrix as well as this D matrix, all three of them are not functions of X. You see here, B is minus 1 over L and 1 over L. So it is important to note that B, D, and D are not functions of X. So pi p, if these are not functions of X, I'm really only taking or finding the integral here over the length from 0 to L, right, of dx. So I can write this as a L over 2 multiplied by D transpose, B transpose, D transpose times B times D. And remember, this term here is for U, right? This is all here, U, the internal potential energy.
Consider this forces may not be so if they are not, doesn't mean the equation reduces down to
Correct. Correct. So if I don't have xb, for example, if xb is a 0, so this term is going to be gone, right? But we're trying to derive it for a general case. So actually, typically, since you mentioned that, Tarzan, typically, these are the ones we're dealing with. But we're also using this opportunity to evaluate equivalent nodal forces should I have a distributed load along the element. Okay? But the most common would be this, the nodal forces, P. Okay? Or at least we want to convert all the distributed load to nodal forces in order for us to be able to apply to the element. So I will come here, and then this is my strain energy, and then I have this minus. And what I'm gonna do here is I'm gonna consolidate. I said we're just gonna make all of these nodal forces. So if you see here, I can take this D transpose, and it's common between the three terms, right? And then I'm gonna say I'm gonna multiply this by F, where I'm gonna make this F equal to P plus the double integral over the surface 1 of NS transpose multiplied by Tx ds plus the triple integral over the volume of N transpose times XB dV. So in other words, I can take all the forces applied on the element and convert them to nodal forces F. So this F gets 3 loads contributions, namely P, the nodal loads or nodal forces. We're trying to differentiate here between F and P. we also get this Fs, which is the equivalent nodal forces from the surface load or the traction, which is equal to the integral over S1 of NS transpose multiplied by Tx ds and Fb, which is equal to the triple integral over the volume of N transpose multiplied by Xb dV. It is important to note that Fs and Fb are based on the shape functions N and S and Ns. And these should be statically equivalent to the original loading. Statically equivalent to the original loading. So they should yield the same resultant forces and moments about any point. So we are able to find the equivalent nodal loads utilizing the shape functions. So you see where the shape functions came into place? Now we are ready to minimize the potential energy with respect to nodal displacements U1 and U2. So step number 3, we're going to minimize pi p with respect to nodal displacements in this case here would be U1 and U2. So we're going to take the partial derivative with respect to U1 and set that to be equal to 0. And partial derivative of pi p with respect to U2 and set it to be equal to 0. Now, when I look here at the equation, you will notice that we have the expression for U, this expression for U. I'm going to let U star be equal to D transpose multiplied by B transpose multiplied by D transpose multiplied by B multiplied by D. Okay. Now let's substitute here a few things. So for this D transpose, I'm going to get a U1 and a U2. For B transpose, here is B, right? So when I transpose B, I will get a minus 1 over L and 1 over L. And here is the earlier question about D. In this case, we said D is simply the modulus of elasticity. This is a one-dimensional element, so D is going to be a 1 by 1. So I'm simply going to put here E sigma equal to E times epsilon x. Okay, does that answer the earlier question? Multiplied by B, So I have here minus 1 over L and 1 over L multiplied by D, which is U1, U2. And this is the quadratic expression. So we're going to get here out of this E over L squared multiplied by U1 squared minus 2 U1 U2 plus U2 squared. So this is this U star. Okay, in our equation, we also had D transpose times F. So this D transpose times F will be written as U1, U2 multiplied by F1 and F2, and specifically we're working in the X direction. So this is equal to U1 F1X plus U2 F2X. So now I'm going to substitute in my potential energy equation. So we're going to have pi p equal to AL over 2 multiplied by this U star, which is E over L squared times U1 squared minus 2U1 U2 plus U2 squared. So this takes care of this term, minus D transpose times F, which is going to be minus U1 F1X minus U2 F2X. Now we can do the partial derivative with respect to U1. And of course, we have an L squared and L. So I get here A E over 2L multiplied by 2U1 minus 2U2. That's it. Minus F1X is equal to 0. And I'm going to call this equation 1. And of course, clearly you see here we can cross the twos together. Next, I'm going to do the partial derivative with respect to U2. And I'll get here AE over 2L multiplied by. I have a minus 2U1 plus 2U2. This will become a 0, and then I have a minus F2X is equal to 0. And this will be equation 2. In matrix form, excuse me? Yes, we can. In matrix form, we can write that as AE over L multiplied by 1 minus 1 minus 1 and 1 multiplied by U1, U2 minus F1X, F2X is equal to 0. 2 zeros. Of course, if we move F to the other side, or write it as F and move this to the other side, we can write it as F1x, F2x is equal to AE over L times 1 minus 1 minus 1 and 1 multiplied by U1 and U2. So clearly, this term here is my stiffness matrix K, which is equal to AE over L times 1 minus 1 minus 1 and 1 as before. So we were able to use the minimum potential energy to find the element stiffness matrix of a bar element.
Like the shape functions aren't just a linear function. That term, so you go to the minimum potential energy, it's always like kind of like a traverse, the derivative set to 0 is always the lowest point, or is there ever kind of like more curves with multiple?
We are minimizing, right? And it is over the element unless you have more nodes within the element, right? It is going to be, usually we are using polynomials, right? So it should be okay. Now, it is worth noting that this stiffness expression, and I think this is included in the appendix, is equal to this A times L multiplied by the expression we got here as B transpose D transpose times B. Okay, just something to keep in mind. So this U, the internal potential energy, is equal to AE over 2L multiplied by U1 squared minus 2U1 U2 plus U2 squared. If we look at this expression, it's coming from here, so we can write it as 1/2 D transpose times K times D or 1/2 D transpose would be U1, U2, and then K is AE over L multiplied by 1 minus 1 minus 1 and 1. This is multiplied by U1, U2, D, right? So we can say that this K matrix is equal to AL multiplied by B transpose times D transpose times B. And this is going to be important. I'm going to leave this as a rectangular matrix because we can use it later on when we are deriving the stiffness matrix for other elements. This expression, the partial derivative of the total potential energy with respect to ED, will give us the AL times B transpose times D transpose times B multiplied by D minus F is equal to 0, where the stiffness matrix is given by this term here. This would be the stiffness matrix of the element.